Yes. So I have my point, which is epsilon flexible. I have its stable manifold. That is for F. And so I will not put the period, so I will put F instead of Fk. So I look at my dynamic. So on the first fundamental domain, I don't change for the moment the dynamic. But, okay, I know that I can, by a slight perturbation, I can linearize diffeomorphism close to the fixed point.
Are you proving this?
I am proving this.
Doesn't seem very difficult.
Sorry?
No.
Don't see it very difficult?
No.
Okay.
But you want something.
So, okay, so you put it mostly linear. So I focus in the part it is already linear. But now you have a deformation of this linear map. And so very far you put this linear map and slowly you follow the isotopy. So you just, when you go in R2, very far you put your linear map and you have an isotopy of linear map and you start to put the isotopy and that makes you a diffeomorphism. So I can assume that all in my path, all the linear applications that I had, I will have realized as a diffeomorphism. And as all these applications were epsilon close, I get that as a diffeomorphism which is epsilon close of the previous one. So by a small perturbation, I get a diffeomorphism which has this property. Far, it's just F. Then I have a place by round circle where it is an homothétie. Here you have, so F tilde is lambda 0, 0, lambda. And there, here, it's with a strong stable, and here 1. But it's contracting. I want it still contracting, but with 1. But I have a place where it is homothétie. And the nice thing is that if I decrease this part to making so small that you cannot see anything, that don't change the distance because homothétie don't change the C1 norm. So you make a conjugacy by a homothétie, you shrink this part to almost a point, and that don't change the norm. This means that here I can assume I have plenty of fundamental domains for my homothétie. So here I have m fundamental domains. And m is the number for any m. I can do that with no changes. The same outside, the same inside, but in a very small scale. And here I put many, many fundamental domains. Why it is useful? Okay. If you consider R2 divided by an homothétie, it's a torus. When I choose a curve here, my curve gamma, joining a point to another, when I look that in the quotient, I get a curve in a torus. My curve gamma is any curve. Okay. Gamma, the projection here on the quotient dynamic is a torus. And this curve is the image by a diffeomorphism of a straight curve. And then there is the fragmentation lemma, which says that every diffeomorphism is a product, isotopic identity, is a product to a finite number of diffeomorphisms epsilon close to identity. So I have some here, I have some phi sending this straight line on that, and I write phi as equal to phi 1 times phi 2 times phi, I don't know how many, big N. Okay? And these ones are Each one is epsilon close to identity. So I will put phi 1 here, phi 2 there, phi 3 there, phi 4 there, and so on. On this straight line, we'll follow, when by iteration, we'll take phi 1, then phi 2, then so on. And when it cross the homothetic region, it is my curve gamma. So that is the proof. So the proof is to use the C1 topology for telling that you can make as much as you want as homothetic fundamental domain, and to use the huge number of homothetic fundamental domain for slowly transform your curve to the curve that you want by making a small perturbation on each fundamental domain. Okay. So that's the proof, so I will not. If someone wants to understand and want to make question, it's a good time. And otherwise, I just explain how to use that. Okay, let's go to how to use that. So the first things we have done was not to get the aperiodic classes, but to see that our setting allows us to expel saddle with trivial homoclinic classes. That is not so easy because you need something for checking that your saddle cannot have in the homoclinic intersection and is not, do not remain in your class. So how you do that? You have your rectangles of your Markov partition, you have your flexible point. Let's say that X is a flexible point. And you want to eject X. How you do that? Well, you look at all the intersection of this cylinder with the image of the other. So you have the intersection by itself, okay? And you have plenty of other intersections here, which are cylinders. You don't know what is the shape of these cylinders, okay? But you have plenty of cylinders there. So let's look at all is a product. Let's look at just the stable manifold. So you have your point. It's the image of the disk. And here you have several things that I will consider as obstacles. And I have, so my point. Now you will choose my future stable manifold as something which avoid the other images, like that. And I say, yes, by a small perturbation, I can get a diffeomorphism on it so that this disk is still a contracting disk, but the strong stable is, I don't know what it is there, but it is precisely that curve. That is what the flexibility gives me. I can choose it, and I choose, so that is disjoint from the other intersection of the rectangle with this rectangle. Okay. Now, at this point, as a derivative here, which is 1, I can make a flip bifurcation. So I will have not flip, I can make a bifurcation. I can transform the derivative so that this will be expanding, and I will be two other points having their stable manifold following this one. Okay, it's not important for me. These are the two other points because these other points have two-dimensional stable manifold, but this one now has a one-dimensional stable manifold. its stable manifold is disjoint from all the rest of the dynamic because it is avoiding any return. So this point now is outside. I just expel that point. And that is robust because I have a fundamental domain of its stable manifold, which is disjoint from the chain recurrent class of the other. And in fact, you can see that this point here, you get this repelling region around this one that make a new filtrating set, which is where you have your point and not the initial point of your Markov partition. So you truly put this point out of the class of the rest of the dynamic. Okay, that's a way for making a saddle outside.
It's repelling, yes?
Yes, I put a non-stable manifold to this point, a small one. So I had a point which has a stable manifold on 1. Here, the ion value was 1. So I transform this point. It was attracting. So after perturbation, you put 1 here with still attracting. And the other, which is this point, become a saddle. Okay? So, like that, I put outside the saddle point. But it's not that we want. What we want is to put outside hyperbolic set, non-trivial hyperbolic set. We want to expel non-trivial hyperbolic set that we choose for choosing by induction the limit dynamic that we will have. And so, let's put the two theorem now. So, I will call homoclinic circuit or graph, I don't know circuit. If it's understandable, I keep the name. It's finitely many periodic point, finitely many periodic orbit, union xg, finitely many heteroclinic or homoclinic orbit. So, this circuit is you take some points. So, indeed, in my picture is like that. And you take, so you have your periodic point, and you take some intersection. Like that. And the unique, so let's call that gamma. And the unique that I want is that gamma is chain recurrent. Meaning that you can, everybody is connecting with everybody. So, the theorem is this one. The main tool for building our periodic class is that. So, theorem. So, we have the Ri and so on, F, and we have the property P. Property P. Then, for any gamma homoclinic circuit, what we need is that the Pi are epsilon flexible with large stable, okay, or any circuit. There exist, I think 4 epsilon, but I will put epsilon or 4 epsilon perturbation. So there exists G 4 epsilon close to F. We support G is equal to F out the Ri. In fact, it has to be small in a small neighborhood of the circuit. Okay, and so what we need is that now gamma, so that gamma is still a circuit for G. But gamma is, so here I had a point, a periodic point PF. So gamma is not in the class of my point PG now. So I put outside, in fact, all the neighborhood of gamma we can put outside the class. We can eject, what we will eject is a basic set in a neighborhood of gamma. We will have a basic set out of gamma which will be outside, and exactly as in the case of the one periodic point. In one periodic point I was ejecting one point but creating two parallel orbits. Here we will have an hyperbolic set that we will triplicate. In the middle it is ejected and it has two parallel hyperbolic sets we survive in our chain recurrent class. Do I have some minutes? No, 0 minutes? I have some minutes? Okay. So.
At least a minute.
Okay. Oh, okay. I'm erasing the theorem, but let me explain in a very.
Almost half an hour. Yeah, 25 minutes.
Yeah.
If we make it shorter, would not be forced to run to the university.
Okay, you appreciate if I make shorter. So I think I can make shorter. Anyway, it starts to be technical, and so as I tell you, it's truly something I think very difficult. So let me explain when the circuit I want to expel is just one periodic point on one homoclinic orbit. So if you look at, so I have my point X or P, and I look at some return of my cylinder crossing here. So I have here Q, which is, so Q belongs to the unstable manifold of P intersection to the stable manifold of P. I take some, the first time it arrived in my stable manifold, and I would like to put outside, so here if I take the local dynamic around the periodic point on the homoclinic orbit, I have some small basic set, hyperbolic basic set, and that is the one that I want to push outside. How to do that? I know that I can choose my stable manifold here as I want. As I want to expel this one, also, I want that it remain an homoclinic point, so certainly I will want that this manifold pass through that point. Okay. But I have some difficulty, is that if I make some change here, when it's returned, I have the same drawing which appears here in the return. So if I choose my stable manifold here, I get some drawing there. Okay. And I want to expel a basic set around that. So what I need is to get, so the game consists in finding a perturbation of my dynamic so that the strong stable manifold of my point for the moment, so will be with some eigenvalue 1. And I want that if you look at this strong stable manifold here, and you look at, okay, it will pass there somewhere, and you look at its image. So here we have two dynamics. We have some kind of iteration function system. That is, we have this, which is Fk, and then I have this cylinder. So that will be a transition from here to there. What I call transition is that I have my cylinder. So the cylinder is going inside itself by F, by Fk, or by the period. But you have also that some return of this one. You have this one that after some moment return by T there. That is a second return. So I have here in my disk, if I follow by the holonomy, the strong unstable holonomy, I get a map here which is drawing what I have here. So I have these two dynamics, and I want something, a curve which is invariant by both. I want a curve which is invariant by, at the same time, my contraction, Fk, but also by my transition there. So that I will have, like that, an horseshoe drawn here inside the curve. Okay. That is what I want. And for that, I can, so in fact I don't need that in the middle they coincide. So what I want is that if I take the whole picture here and I draw here, I will have, as I will, let's put another color, so that is my stable manifold. Let's take T of this stable manifold. I want that they coincide in the neighborhood there. But what I want is where they do not coincide, it's outside the dynamics. That is, there is no, the part where they are not coinciding is the part which is out of the filtrating set. Okay? So that's a little bit difficult in general to find some invariant things by some process with not having an operator, a fixed point, and so on. But we don't have because it's not unique at all. We have to build by hand. And so there is a difficulty is that when you want to, for example, we have the same obstacle at the first things, we have the other intersections there. So our curve cannot be simple, it's a complicated curve. So when you take the image here, it's a complicated curve. Okay? But for getting a complicated curve, you need a certain number of fundamental domains. And if you say, okay, here for getting the invariance, I need to make it more complicated, you say, yes, but in that case, I have to increase the number of fundamental domains with homothétie. So we need to have some a priori bounds of the number of fundamental domain of homothétie we will need for getting this kind of invariant curve. So you have to check that we are looking our curve in some as a graph with some prescribed Lipschitz conditions, so that we know that it is enough to get a given number of fundamental domain for having this curve. Then we will require here the coincidence is a very, very small interval. So this interval indeed corresponds to the part where, so you have here the fundamental domain, then you have a part where the curve is complicated, but you have a part where the curve here has to be very simple because it's just just an unstable manifold as a point. So we will have this coincidence where the stable manifold will be like a straight line. So the image will be a straight line, and that is not too complicated to have the coincidence. There is a complication with that for making that, we have to deal with this part where the dynamic is not at all an homothéty. Here we have 1 as an eigenvalue. So if you look at the obstacles, there start to be like this one, that I know that my curve will cross this obstacle. This obstacle will be like that. And so when I arrive here, what I need with this picture, when I have my obstacle which arrives here like that, what I want is that my curve arrive, enter between 2 and start to cross to coincide to my curve directly. So you see there is a very difficult game there. For that I tell you at the beginning that it was the most complicated part that I have ever done. And I'm happy to have the opportunity to enter there so that I recover for myself the whole proof. Now it's my mind. And so, okay. So what we do is, okay, we have a game to know how you do for getting this invariant curve. Let's finish by explaining why that solves the problem. So the affirmation here was, okay, I have the other intersections that I don't care so much, that is not difficult. I have the neighborhood of my homoclinic point, and finally I succeed, let's say, to have my curve which somehow coincide to its image by the transition here. On outside, don't touch the images of these obstacles. So I know that this small thing is some invariant dynamic, but here, at this point, on only that point, the derivative is 1. In the other place, I don't know what is the derivative. But that was only an homoclinic point. So all the dynamic spend most of the time here. So this invariant curve, so that part on this small one, if I look at the normal derivative, is mostly 1. As it is mostly 1, I can just poof, like that. So I, again, make the same trick here and here, so that is the image of something like that. And we check that, doing that, the place in the middle is separated from the rest of the dynamic by a filtrating set. So we expulse some horseshoe. So we have, from the whole dynamic, we put outside some small horseshoe around this graph. And then we will use the flexibility of my periodic point for recovering all the properties that I said in the beginning about having a Markov partition with some point of some index, some point of the other index, some complex eigenvalue. And then we can continue. And so now for getting the aperiodic classes with the dynamics that we want, we just need to choose a circuit with prescribed properties. Like you can take the periodic orbits passing in every rectangles or avoiding some rectangles or something like that. And so you choose by induction a sequence of circuits, each time circuit of the previous one, so that at the limit you get the announced properties. And either you don't clap so that you can still have a rest. Slowly.
Approximation mentioned it was only in C1. There is no hope for getting anything like this in any higher smoothness.
So I get that the result, yes, but the technique, no. That is, here is, as we started to see that flexibility is truly a C1 property, after that, you don't care, you are obliged to make C1, so you do C1 everywhere. So we have made a typically C1 proof. But I remember the time we have made universal dynamics. Okay, we announced universal dynamics, I think the same year, to have announced that it makes C2. So that is, I think that there are people with other tools, certainly more complicated than this one, which is already enough complicated. But I think the result is true in any setting. You can have generic aperiodic classes with very strange dynamics.
Thank you very much for the whole mini-course. Achievement.
Thank you for the opportunity.
Print out.
Oh, yes, I sent you the second one.
You sent it?
I already sent it. I think. Sorry?
Do you want to?
Yes. So maybe you can speak.
I will print them all.
Solutions to all hedge problems.
We may done in 5 minutes, is that?
As soon as possible. I come
So technically I have
after this.
also I have keys to my room, but I'm already up and they've cleaned it. So I have nothing else to do.
So you will go? So you will go?